Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this video, we'll continue a series on college algebra that's embedded into a trigonometry course. It is assumed that you have seen all of Algebra 1 and Algebra 2, elementary and intermediate algebra courses, so you should have a very strong knowledge of functions and all that stuff prior to this conversation. However, as a review, we're still in the middle of talking about functions. And some point in this topic, we talk about rates of change and the behaviors of graphs. So specifically, we're going to talk about intervals of increase and decrease, mainly because those end up being hugely important as you move forward in the STEM fields. So let's see. The very first subsection we're going to talk about here is using a graph to determine where a function is increasing, decreasing, or constant. So you could see by this definition, and I'll just read it out loud, we say that a function is increasing on an interval. I'm going to highlight that word increasing. Why not, right? I have a highlighter. If the function values increase as the input values increase within that interval. Now that's a very, still non-rigorous definition, but a very fancy way of saying if you can read from a graph, or maybe I should say it this way, if the graph of a function rises from left to right, we say that it's increasing. Now that's a very layperson's definition, and since you're heading into calculus, is my guess, we want to be more rigorous with that definition. So we've gotten slightly more rigorous with this definition right here, saying that as the function values increase, or if the function values increase as the input values increase, then we know we have an increasing function on that interval. We also say that function is decreasing if the function values decrease as the input values increase on that interval. So you can imagine the input values will increase, the function values, which are also known as the y values, will decrease, and you can see from left to right that graph is falling. Now, a lot of people find this to be a very easy definition to kind of digest. And just for symmetry, I'd like to go ahead and highlight the word decreasing. But as you move again towards calculus, the definition gets much more intense, mainly because you really want to be clear when you're talking to somebody about something in mathematics, which definition you're using and how much detail you want within that definition. So finally, we say that a function is constant if it's neither increasing nor is it decreasing. And actually, I don't even think that's a good enough definition, but my caveat here is it's still the non-rigorous definition. So if there's a teacher watching this, you should immediately want to call me out on that last sentence, saying that a function is constant if it's neither increasing nor decreasing on an interval. That's actually not true, because if you look at the sine curve from negative infinity to infinity, it is not increasing on that entire interval, nor is it decreasing, yet it is non-constant. So that aside, if somebody doesn't understand that, that's okay. It's not that big of a deal. But really, a function's considered to be constant on an interval if its values on that interval never change. That's probably a better definition. So maybe I'll write that in. So there you have it. That's a little cleaner definition. So it's considered constant if its values do not change on that interval. So let's go ahead and see this in action. Often when we're dealing with problems like this, where you're given a graph, and that's what this lecture is about. You're given a graph, you want to determine if the function is increasing or decreasing on the intervals showcased in that graph. Well, generally speaking, a lot of students just kind of rocket through this. If you're using an online homework system, stating the intervals of increase or decrease are going to be a little bit tricky if they don't plot points. So just to give you a heads up about that. So let's go ahead and use highlighter colors here. So I am going to go ahead and use blue for decreasing intervals. Or it's actually, I'm going to use blue for to showcase the y values where the curve is decreasing. And I'll go ahead and use yellow to showcase when it's increasing. Just as a heads up, just highlighting stuff on a piece of paper is not what your professor wants. Your professor wants something a little more rigorous than you just drawing a picture. But I'm just doing this so that I can showcase the intervals of decrease. You can easily see that function is decreasing from negative infinity, even though some people will look at that and say that's x equals negative 0.2. That arrow means as you go to the right, the function continues to, or sorry, as you go to the left, the function continues to rise. So therefore, your x values go to the left forever. And so this function is falling from left to right from negative infinity all the way to positive 1. And then you can see it also falls from x equals 3 to x equals 4. Again, these are approximate values. So it's very important if you're using an online homework system to be kind of careful. Zoom into pictures, right? Really check to see if that's the interval of decrease. Now remember, I reserved yellow for increasing. You could see it's increasing all the way up to, well, maybe I should say from 1, x equals 1, all the way up to x equals 3. And then again, from x equals 4, yep, it goes to infinity, so all the way to infinity. Now, that's fine and dandy, but what I've actually done there is I've highlighted the y values. And generally when you, or not generally, always when you state intervals of increase or decrease, they're x value intervals. So let me go ahead and take those shadings that we have there and transpose them or move them down to the x-axis. So you can see here, I'm highlighting that the curve is increasing from 4 to infinity. Also, the curve is increasing from, 1 to 3. And we know that it's decreasing. Again, I'm only highlighting the x values where it's decreasing or increasing. Decreasing from 3 to 4. And finally, it's also decreasing from negative infinity all the way up to positive 1. The tricky thing about interval notation and intervals of increase and decrease is that you need to know that, rigorously speaking, so technically speaking, you should not include endpoints on those intervals. That is, intervals of increase and decrease are open intervals. Now, there is an actual reason for that, but that reason comes from calculus. So the main justification I'll say here is, and this might fall flat for some people, the reason why you don't include the endpoints, for example, the reason why if somebody asks me, oh, what intervals is it increasing on? I would not say, so I'm going to use red here. I would not say, oh, it's increasing on the closed interval 1 to 3, union 4 to infinity. Notice you never put a bracket on infinity because infinity is a concept, so you can't actually grab onto it and say I've reached it. The reason why you would not include the 1, the 3, and the 4 is because you're not increasing exactly at 1. In fact, at x equals 1, according to this curve, you're neither increasing nor are you decreasing. You're at a flat point on the curve right here. So at that point, if this is a roller coaster, you definitely would be falling, 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 falling. And then right here, you wouldn't be neither falling nor rising. But then here you're rising, 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 right? So what's important to note is that at those edges, you are neither increasing nor are you decreasing. That's a calculus concept, but still, it's important enough that I'm a stickler for that. And I have noticed again, I keep mentioning online homework systems because I used them during the COVID crisis. For my students, normally I don't like to, but I'm just using them right now because of the fact that we need some way to get you practice, right? So in online homework systems, I've noticed that a lot of authors will code questions incorrectly. They will include the endpoints on intervals of increase or decrease. That should never be done. So if you find that if you're working on an online homework system and they've included the edge points, you should contact your professor and let them know, and then that professor can either fix the question themselves if they coded the question, or they can contact the author of that question. Anyhow, that function's increasing from 1 to 3 and then 4 to infinity. It's decreasing from negative infinity, right, all the way up to x equals 1. And then union, it also is decreasing from 3 to 4. Remember, union just means you're adding a little bit more to that interval. So as far as intervals of increase and decrease generally, I know I spent a lot of time on this, but the reality is it's pretty fast. A lot of students are pretty rock solid on intervals of increase or decrease if they're given the graph of a function. On the other hand, if they're not given the graph of a function, well, you generally need calculus. We now reach a concept that is actually massively important in calculus. The idea of a local maximum or a local minimum is just kind of dominates a significant portion of Calculus 1. So let's talk about this. A value of the input, so an x value for most of us, where the function changes from increasing to decreasing. Let me draw that before we read the rest of that. So we have these inputs here, and they told us we have a function that goes from increasing to decreasing. I hope you realize that that's the point right here, where the function goes from increasing to decreasing. Maybe it has an x value of a and a y value of f evaluated at a. And again, the x value is a. So, going back to the definition, a value of the input, or an x value, where the function changes from increasing to decreasing, as we go from left to right, is the location of a local maximum. So this point right here would be called a local maximum. I'm going to write that in here. And there's so much subtlety with this idea, even though visually it's kind of obvious. Oh, that's the highest point on the curve right there. There is so much subtlety behind it. It's just pretty crazy. You require a lot of calculus for that. The function value at that local point is the local maximum. So I often say I have a local maximum at a comma f of a. But if somebody says, what is the local maximum? We often say it's just f of a, right? So if that height was 5, we'd say the local maximum is 5. Actually, maybe I should put actual numbers here. What if I told you the input here was 3, but the output was 5? We would say the local maximum is 5, or the local maximum value is 5. We have a local maximum at 3, though. So maybe I'll write that down. It's just a subtlety in language. So when somebody says, what's the local maximum? It's sort of like saying, what's your maximum salary? You don't tell them the year that you get it. You tell them the maximum salary. If they said, when did you get your maximum salary? Then you would state the input or the year with which you got that maximum salary. Now, along the same lines, zoom out a little bit. A value of the input where the function changes from decreasing to increasing, well, that's a local minimum. And just to showcase that, draw this out. You go from decreasing to increasing. Well, where that shift between decreasing to increasing happens, that is called a local minimum. And that, again, tends to be somewhat extremely obvious for people. Together, local maximums, I already started using the word, local maxima, which is a plural of maximums, And local minima, again, the plural of local minimum, are called, when you group them up, the local extrema. So these two, if they were existed on the same function, so if it looked like this, the collection of those 2 points would just be called the local extrema. It's sort of like saying you have this roller coaster and you want to find all the local extremes. Well, that's all the highest highs and lowest lows, right? Or the highs and the lows, maybe I should say. So this kind of rounds out this topic. It's very fast, even though I took quite a bit of time with this, but that's my style. I generally spend a lot of time on a problem just because I want to make sure that people are with me. But let's state the local extrema for the problem in example 3.3, number 1. In other words, the very first example in this talk. And that would be this bad boy right here. This example, we want to go ahead and state where the local maximums and local minimums are. Let's start with local maximums. In fact, I'll write that down here so that we know what we're aiming for. And often, just to let you know, people will often say local max, or what I do is I call them L maxes. And so this will be a list. In fact, maybe I should put a colon there. It'll be a list of points that are my local maximum points. And if you look at the graph here, you're really looking for when it switches from increasing to decreasing. And you can see right here, it switches from increasing to decreasing right there. So I know that that point is a local maximum. So I'm going to highlight that point right there. Also note, this is kind of the tough thing about graphs that are handed to you. If they don't align to a grid perfectly, you cannot say that y value is 1. It's slightly less than 1. I will be somewhat, try my best to be somewhat exact with it. The x value is 3. And the y value is likely 0.95 or something like that. So you don't want to be too far off from the actual value. So don't just say 1, like use a little common sense there and just read it properly. So that is the only local maximum I see, which is 3, 0.95. And then we talk about the local minimums, and again we'll call those the L mins. So let's go ahead and zoom in here. Here's an interval, or here's the function where it goes from decreasing to increasing. That point where it switches from decreasing to increasing, again, that is called a local minimum. And again, that's not exactly at a height of -1. It's at 1, maybe a -0.95. I'll have that symmetry there because I want it. If I zoom out a little, you'll see there is actually a second point where we have a minimum. Looks to be right about there. If I zoom in, you'll notice that's not exactly at 4. It's slightly above. I'll say it's 4.05. Why not? And then the y value, well, it's definitely not at a half. It's slightly above a half. So let's say it's at 0.6. Notice how I'm trying not to be too far off from what the value is. So I don't want to make a wild guess and say it's a 0.5. I think it's slightly higher than that. So 4.05, 0.6. Those are my two local minimums. 1, -0.95 for symmetry there. And 4.05, 6. I want to provide a little warning here. Some people will write these 2 points and they'll say, well, I'm just going to glue those points together. And so they'll write it like this. Oh, that's 1 to -0.95. And I'm going to union to that 4.05, 6. So it's 1, -0.95. And they glue to that another point. Well, this is improper notation on multiple levels. First of all, this black ink that I'm pointing at, those are 2 points, not 2 intervals, but 2 points in space. If you were to hand me this red ink, that's 2 intervals. You glue together intervals via union. You don't glue points together via a union. And so don't use the union notation when you're dealing with points. If you have a list like this, like a list of points, you would literally write it as point 1, comma, point 2, right? You would list them out as ordered pair 1, comma, ordered pair 2, all the way down the line. So I just want to mention that that's a terrible notation that we've adopted for intervals and points. It should have been that we adopted some other notation for points, to be honest with you. It would have been better if we had learned points like this. That would have been much, much better, because then there would be no ambiguity. Unfortunately, that's just how life works out. Sometimes people make a decision without knowing the ramifications. The last thing I want to mention here is something that throws students off initially. When we're talking local maximums and local minimums, you require, for example, with the local maximums, that the function is increasing on one side of it. It's increasing on one side of it and decreasing on the other side of it. That is a requirement to be a local maximum. It's increasing from the left and decreasing off to the right. Same thing for a local minimum. It's decreasing from the left and then increasing on the right. That is critically important, because when you get to calculus, you'll have some functions that you're working with that, I'm going to draw something off to the side. You'll have a function that you're working with that looks like this. And then that's it. Like, let's just say that that's the function there. So it's closed end. It just stops at, let's pretend, 1, and it starts at 0. And so a lot of students initially in a calculus class will say, well, 1, there must be a local max at 1. There is not a local max at 1. To be a local maximum, it must, by definition, be increasing from one side and decreasing on the other. But it's not decreasing on the other side. It just doesn't exist on the other side. So that is not a local maximum. So that's one piece of information I want to throw out there, that if your function just stops, then that's not a local max, nor is it a local min. We just would not call them either of those. So that's one thing I want to mention here. It's not going to be important, honestly, in your trig or college algebra course necessarily, but the other piece is important. I will often have students say that it has a maximum, like this curve right here, will have a maximum, let's say, 5.2 and negative 0.1. Remember, to have a local maximum, it must be increasing on the left and decreasing on the right. This is definitely increasing here, increasing from the left, but it's not decreasing over here. So that is not a local maximum. Also, I just have to note, if it were a local maximum, what's its value? Is it 4? Right? Is it this height right here 4? No, because the arrow is saying it goes higher than that. It goes up to infinity. And because it runs off to infinity, there's actually no maximum anyway. But that's just a little aside that people, when they're first introduced to this concept and we start going into calculus, people tend to overcomplicate things and say, well, then it must be a maximum there and there. That's not true. There's no max. If it doesn't become a finite value, there's not a maximum. All right, that's all I really wanted to say for this video. It should have been faster than it really was, but I love a deep dive into concepts, and the more you think about increasing and decreasing functions and getting your hands into the guts of mathematics, the better off you're going to be to move forward and be successful in mathematics and science and engineering.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.